Welcome to part 9 of our video series in support of hypothesis testing. In this video, we are going to discuss the goodness of fit test. I'm Renee Clark from the Swanson School of Engineering at the University of Pittsburgh. Okay, so thus far, we've tested hypotheses about population parameters, right? Quantities such as the population mean mu, or perhaps a population proportion, or the population variance, or the difference in two means, or the ratio of two population variances, right? Or maybe the difference in two population proportions. Okay, so we've tested hypotheses about parameter values. Next, we are going to test hypotheses, but not about parameters, but about data distributions. Okay, so specifically, this type of a hypothesis test asks a question such as, does my observed or sample data that I have, does its distribution follow a certain, we'll call it theoretical or hypothesized distribution? So for example, does my observed data that I have follow, say, a normal distribution? Or does it follow a uniform distribution? Okay, or any other distribution that exists, exponential, for example. Okay, this type of hypothesis test is known as a goodness of fit test. Between two distributions, those two distributions being my observed or my sample distribution, the sample of data that I have, versus some theoretical distribution that I'd like to compare my sample data to. Let's look at the example of tossing a six-sided die. Okay, now with a die, the outcomes have a uniform distribution. Okay, assuming the die is fair, leading to an equal probability for each side of the die to occur. Okay, in fact, these outcomes have a discrete uniform distribution, okay, because of the six distinct or separate sides of the die. Okay, so let's say we wanted to investigate this issue. Okay, we would begin with the null hypothesis that our outcomes have a discrete uniform distribution, meaning that each face of the die is equally likely to occur. Okay, so the probability function for a fair die looks like this. F of x equal 1 over 6 for each of your 6 distinct outcomes, okay, or 6 sides of the die. Okay, so in this probability function, there are 6 equal probabilities, okay, each worth 1/6 each. Okay, so let's say we toss a die 120 times, and that die is in fact fair, okay, or we hypothesize that die to be fair, or that the outcomes have a discrete uniform distribution, okay. Then we expect, okay, and this is a key word, we expect each face of the die to appear 20 times, okay, as shown in the table, okay, which we would obtain by taking 120 over 6 for 20. Okay, so that's what we expect. Okay, now, what we actually observe, though, when rolling that die may not exactly match what we had expected. Okay, so a goodness of fit test is going to explore the differences between what you expect and what you actually observed. So for example, for outcome 1 or face 1, we, in this case, did in fact observe 20, and we expected 20. But for face number 3, we actually observed 17, although we expected the 20. But in other cases, for face 6, for example, we observed more than 20. Okay, so each of these columns does add to 120. Okay, so a goodness of fit test that I have abbreviated right there is going to explore whether the differences between your expected and your observed frequencies are due perhaps to chance, okay, or alternatively, whether they're due to the distribution not being uniformly discrete, or alternatively that the die is due to the die not being fair. We wish to thank the National Science Foundation under Grant 233-5802 for supporting our work. Thank you for watching.